to week 11. We had seen Green's theorem in plane for 2 dimensions. We had proven for curl form of it last time, but we didn't give examples to it. So we will do that this week. And then we will also see the divergence form of the Green's theorem in 2 dimensions. Then move on to 3-dimension representation of the divergence theorem. So it's so-called the Gauss theorem. And then we will see the Stokes theorem and wrap up the vector calculus and integral section of our course. Now, so we had said there are 2 fundamental integral theorems of vector calculus, Stokes theorem and divergence theorems of Gauss. And Green's theorem is the in-plane version of it, like 2 dimensions and in 2 dimensions, and sorry for that. And it has 2 forms. Okay. So one is the curl form and the other one is the divergence form. So let me remind you what we had seen about the curl form, and then on the same notes page I will move with the divergence form, and we'll come back to the definitions I have on the slides later. So let's see. Now previously we had seen that we could define a vector field in a plane and a curve in that plane. And if I'm looping around a closed curve like this in counterclockwise fashion, I could be able to find the line integral, obviously, if I know the position vectors. But and the important thing is, am I against or with the field in this case? Well, I can find that by dot producting my vector field with the position vector differential, which is the tangent to this curve. The tangent to this curve, how is it aligned with the force field? So the dot product gives me the alignment. Okay, and now in addition, and there's no addition, yeah, we had partitioned this curve into 2 in xy directions, axes, and then came up with the 2 with a formula on the let's say the left hand side. In general, we put this on the right hand side. It doesn't matter. That this line integral, which kind of represents my work, it can be viewed or it can be worked out as the 2D curl of my field vector. So that's important and gives me a handy tool to convert from a line integral to just a double integral, which could be easier sometimes. Okay, and even more, we have a better understanding of what's going on and how the term or the operator curl relates to the other integrals and so on. So on its own, curl and divergence doesn't mean anything because they are defined with respect to points. But we're not always dealing with points. Just we're dealing with the whole bodies of volumes of stuff. Okay, so that's the important thing. Another way to look or prove that this representation with the curl of f is actually true is by slicing our curve area furthermore and looking at the rotations that we have here. So let's have a look. Let's have a slice like from half in the beginning. It doesn't matter if it's parallel to x or y axis. In this case, I'm randomly slicing it from the half. And then I'm turning this loop, yes, this way, and this loop also this way. Both of them are in counterclockwise, but as you see, these two will cancel out each other. So this means that either I'm following or rotating around this or the other one. If I add those rotations up, these two will cancel where the slice is made. The vectors on the slice will cancel each other. I could slice it more. I could divide into 4, for example. The result doesn't change. In all of the branches that I have here, which I'm rotating individually, I have opposing vectors that would cancel out each other. So even if I slice it into 4, the result will be rotating around the curve itself. The details are going to be canceled out. So this means that if I slice it further down to a point where this little slice is around just a point, which is practically not a real thing, but this is the definition of derivatives, integrals. You are used to this idea of getting things smaller and thinking in terms of the differentials and integrals like that. So if I get a very tiny spot like this and many tiny spots like this that forms the whole area, I will be able to think like, okay, I have some rotational thing going on there, which is now defined as curl around the point, and I have defined it this just around this RK, which is the sub unit, the smallest unit I could go, and that integral is now the line integral around this little point. If I integrate them all, obviously I'm reaching the 2D curve of the whole area. Okay, so that's like the baseline definitions we could speak of. And so let's remind it again. A line integral in a field V, vector field, which is equivalent to work, and am I with or against the field, that will give me the line integral, that will be defined as my line integral, and now I'm able to convert it into double integral. As I said before, this could be handy or makes our understanding better. In both cases, this analysis is good. How about the divergence form? What does divergence form correspond to? Now, if you look at the same curve and a similar field, I would have my the velocity, right? The tangent vector aligned like this on my curved surface, and it has two components, like the x, dx, and dy components. So the little segment ds that I have curve length as is the absolute value of the magnitude of the dr. These are stuff that we had seen in 6th week or 7th week. Okay, you can look at your slides and get the definitions of ds and so on from there. But in the curve form, we were interested in what was with respect to the field vectors, how this was aligned. Okay, so we were dotting the dr with the df, but I might be interested in also how my surface normals are oriented with respect to the field. Why is that so? Because let's say I'm going to consider this field as my flux. How come? if I multiply for a physical meaning, for this f to get a physical meaning, I will multiply the vector field by my areal density, because I don't have a volume yet. Okay, divergence form of Green's theorem is for 2 dimensions, so kilograms per meter square. And I know the vector field has is like a velocity vector, so meter per square, and that will be equivalent to kilograms per meter second. Okay, sorry, meters per second. And so if I cancel out one of those meters there, I will end up with kilograms per meters second. And then if I just multiply, this is not a cross product, just a multiplication by ds, I will be able to cancel out one of those meters too, and that will be equivalent to kilograms per second, that is passing the curve at a certain time. So this means that I could define my flux just by defining my field and multiplying it with ds. So this is important. And how do I get the flux that is passing through the curve? The component, okay, the x component of, let's say, my vector field that is like in orange here, x component is just about giving my velocity around the curve, whether I'm with that x component or not. Okay, now I'm talking about the x component of the vector field, not the velocity. So x, I was discussing in the curl form whether I'm aligned with this x component of my vector field or not. But how about considering the other? Am I aligned, or my surface is aligned with respect to how well is aligned with respect to my surface normal? Because that will be the vector field component that would push the particles out of my surface. Okay, that's the only component of my vector field that would push, let's say there's a particle here, push it out of the surface. That's exactly what we mean by flux. So vector field turning into a flux just by multiplying it with ds, and I'm gonna be able to understand some things from the divergence form by looking at it. So taking the line integral around it, we were previously dot producting it with the tangent vector. Okay, now I'm going to for the flux integral, line flux integral, I'm going to multiply it by the normal vector. Okay, dot product it. I'm going to dot product my vector field with my normal vector of the surface, so that I will be able to find the y component of my field vector on a specific point on a surface, which will be pushing out my particles. So that is represented on the left hand side now. That's it. That's called a flux integral, and in this specific case, two-dimensional case, it's a line flux integral. That's not a proper wording in mathematics, but we can take it like that. And on the right hand side, I'm going to claim that it will be equal to divergence of f at this time. Okay, divergence of f from that surface. So how come this becomes, and this is obvious, okay, there's no question mark here actually. The divergence of f is defined as the first component derivative with respect to the first variable and second component with respect to the second variable. This is definition of divergence. There's no problem with that. But why it is divergence, we don't know it yet. And on the left hand side, I'm going to represent this this f dotted with the surface normal as this little thing here, p dy minus q dx. And depending on our previous definitions, we will move on from here. Now, where does this come from? F dotted n ds. How can I open this up? P component, Q component of my vector field, and this will be my and I need to now find the representation for the surface normal. This I can do easily. Now let's have a look at the tangent vector on a random Cartesian coordinate. So I have dx and dy, and my surface normal is supposed to be at right angles to it, right? Right angles to it. So I'm gonna have to rotate this vector clockwise, and that will be some velocity vector that is pointing just normal to my surface now, but it has a dimension. So for a unit vector, I need to divide that by its dimension, which is ds exactly. So this vector dr has a dimension ds that we had put before. And to normalize my normal vector, it has the same length. I will divide it by ds. But how do I do this rotation? This I think I have talked about maybe 2 lectures ago, somewhere around there. Please remember or go back to that, or just learn it from here. If I have a dx dy, how do I rotate it counterclockwise 90 degrees exactly? I will swap the components. So dy becomes my now new x axis component for my normal vector, and then dx, but I will take the reverse of negative of dx, and then this vector, this new vector, which is formed from the dr vector, is gonna be my normal vector. Normally we have two normal vectors. Okay, if this was dr, one could be pointing towards the center of the curve, to the curvature. Okay, the other one is pointing outwards. In this case, since I had explained the intuition here, we're looking for some flow that is flowing out. That's just by convention, and the flowing out is associated with divergence. And now I'm interested in only the outwards pointing surface normal. Okay, outwards pointing surface normal will correspond to divergence positive, which is going to be outflow from a point and leaving the point. So these all we will join up. So this is the intuition where this divergence comes from, but how it is actually represented. Now and if you put this n now in, okay, instead of n, if you write dy and minus dx by ds, because I normalize it with ds, so this ds with this ds I will cancel out, and this dot product is just simply p times dy minus q times dx. Okay, this is something similar to what I had driven in the curl form. I need to compare it with the curl form. Let's do that. And let's pick up this dy. Okay, if you look at the Green's curl form, besides dy I have q. What happens to q? I take the derivative of q with respect to x. Okay, so what's besides dy here? It's p. I take the derivative of p by dx then. The other one, I have dx over here. What is happening to the function besides dx in the curl form? It's p. I have to take the derivative with respect to y and put a minus sign to it. So what's beside dx? I have q. And q by dy, dq by dy, I have a minus sign here. Those minuses cancel out. dp dx plus dq dy, that's divergence. So whatever I'm getting with the by dotting the f by the surface normal, it turns out to be a divergence. And since I have already done this job, this tedious job of proving the Green's curl form over here, I'm not gonna explain where this double integral coming from, but obviously the right hand side is exactly the divergence of f. Okay, I could show it with my nabla symbol or also. Okay, it's a dot product. So this is good. The left hand side, whichever that is, and I understand that left hand side is a flux integral on a line. Okay, it can be represented as the divergence of the vector field that is acting on that surface, or the curve. All right, if we move just right on with the divergence theorem of Gauss, you can say this is just a 3D form of the Green's divergence form. Okay, and what was it? Okay, I have divergence of f. It was defined over an area. Now I'm gonna define it over a volume. Okay, a divergence integral is gonna be defined over my volume. And of course, in this case, I will have on the left-hand side, we had the flux integral on a line. We're going to consider the flux integral on a surface, which makes sense because the flux is going to be always moving outwards or inwards from a surface. So this is a more general form that actually, that's why it's the one of the fundamental theorem of vector calculus. Okay, so this is very fundamental. It's summing up everything we had learned until now into one little expression here. And what is the meaning of it? A surface flux integral. So let's say you have a field and you want to know how fast your material is moving out of that field, within that field, out of a surface. Okay. So this is a very general concept that you will use in heat transfer courses, flow courses, and so many other things. And also this is applicable in magnetism and lots of stuff. Okay, so don't worry about it. Just learn it. And now my surface integral, where n is the outward normal vector of the surface S, it's equivalent to a divergence integral in a volume. But remember this, the Gauss divergence theorem is only valid for a closed volume and a continuous volume. We will see those on our slides. So let's move back onto the slides, and we will come back to the 3D form after a while in the slides. Okay, so let's move on because we have seen enough. Now, what was the definition? This is rolling back. Okay, I will on the slides we're still in the curl form, so don't worry about it. Now, for the curl, as my counterclockwise definition, I keep my region R on my left, and that I will call the positive. Okay, that's the convention. So if I had a hole, that's a special case in my region R. If I had a hole in my region R, I still have to keep the region R on my left. If that is the case, for a hole in a region, I'm rotating clockwise actually. So you can read through these mathematical definitions on your own in the slides. It's just to make the math perfect. Okay, and The other expressions for curl form and divergence form are important, especially we will come back to this form over here. Okay, curl form, curl of f dotted with k dx dy. Okay, so where does this k coming from? Let me explain it here so that we will save time later. What's the curl of f in 2D? Where does it point to? So it's a vector and it's pointing in z direction or k direction. Okay, so this means that on the left hand side I have a dot product, and then that dot product is a scalar quantity. So for this scalar quantity to be equal to another scalar quantity on the right hand side, I always dot it with itself, the direction itself. So this is the unit vector pointing up in the z direction. And my curl, I know by definition, if I defined it in xy plane, it is pointing up. It is pointing up. My curl is pointing up in the z direction. So their dot product is actually the magnitude of the curl. Okay, so you could put magnitude parentheses there too. And in the divergence form, I think the divergence form is already in an explained in this dot product ds form previously, so there's no problem here. And these are the, and why do we have a tangent here? So you have to go back to week 6 to understand that dr is actually ds. Okay, so if you want to represent everything in terms of ds, you need to add the instead of just dotting with dr, you need to add the tangent vector, unit tangent vector. So let's see an example. I have, this is a very simple example. I have a simple curve, okay, but remember those definitions are not for something random, right? I need a closed path, yes, but it has to be like a continuous, okay? But it could be consisting of finite number of continuously differentiable connected curve segments. So maybe I'm not going to be able to differentiate this discontinuous curve. So it's like bending 90 degrees every now and then. But I could pull the segments out, okay, which makes sense, and do the integration as such. That's a legit way. Now, for my I have a line integral, and I analyze this line integral. I see that dx and dy are separate, so I could call these minus y squared and xy as my x and y components of my vector field, actually. And that vector field looks like this, and I'm gonna be moving like this way, that way, that way, and that way, like making a square in this field. And I'm wondering about how much work I'm gonna be doing by rotating like this. Now, sorry. So this is the Green's theorem. Let's solve it with the curl form first. So we need to define these as u and v, and for the right hand side I can take the first derivatives and put them into my double integral here. It will be 3/2. So you can look at this on your own. I'm not gonna literally spell out every operation there. Or you could look at it with the divergence form too, which is just taking the divergence of the vector field, and that will be 3y's, okay? And if you do the integration, it's a very similar operation. It ends up with 3/2. So the idea here is both divergence and the curl forms are equivalent. Could I imagine other way around? I couldn't, because it's simple. I'm dealing with the similar functions here, okay? And And that's it. That's the conclusion. And maybe what would be difficult? What's the advantage? Now this is my vector field, and I'm trying to get a line integral. So what do I need? I need the representation of this curve actually, okay, to be able to plug it into this line integral. That's not always the easy thing, and that's when the this corresponding curl or the divergence form is handy, because taking a double integral over an area for segments or for a continuous curve is sometimes easier compared to compared to compared to taking a line integral over a tedious curve equation. And you could also use this, obviously, to find the area of a region. In this case, this is as simple as it could be, but you can imagine that I could have a curve that is in two dimensions, making a kind of a floating area which doesn't have really proper geometrical features. In that case, how do I find the surface area of it? Okay, you don't always have, we didn't always have computers for this, and there was a nice tool, mechanical tool, which was doing this job actually, but based on what we learned from the Green's theorem, okay, into the space. So this is a random trace that I make, and if I'm not going to explain how this works. There are some counters here, and you can read those counting numbers and make it out by putting into a formula actually. And the tracer, as you trace your curve, the area of which you're interested in, the numbers over here will give you something meaningful. But check the example on example 2 on page 436 in your book. That's a good or not good. It's the same deal, but it's putting in a little bit more definitions in, so it makes more sense maybe. Okay, so how come I can manipulate a line integral like this and change it and find the area? So the area is defined as 1/2 of a line integral like this. So I'm not going to go into too much detail, but the idea here is this. If I define two functions like u and v, which was supposed to be my vector field, which is the case over here, right? Vector field. But their derivatives, if I get some integers out of those derivatives, on the right-hand side, they would correspond to an exact area, maybe multiplied by some factor of my area, right? In this case, if I select those as randomly like x and y's, their first derivatives will be 1 and 1. So on the right hand side of my equation, that will just be my divergence, and it would correspond to 2a's. Okay, so if I'm representing it in A. So by moving along this tracer and noting that I'm moved by dx dy, I will be able to calculate the amount of area I'm scanning actually. And that's the idea. So the line integral over here has turned to an integer valued area on the right hand side. So this is a generic way of finding areas actually by line integrals. All right. And how about the curl form? In the curl form, maybe I I could have put another function like minus y. And in that case, this would again be 2a's, okay? And so on and so forth. Well, this is some field like this, and you could look at this example in the polar coordinates. I'm not gonna deal with it, but one thing that is obvious is if this expression is 2a's, if this expression is 2a's, obviously these are sharing their halves. So my a is either this or that. So that's what I'm telling over here. Okay. And maybe if we do some questions in the homework or the exam, this will become more clear. So you can expect some questions from this point. Now, let's have a look path independence and its relationship with all we have learned here. Now, sorry. If I if I want to evaluate the work done by this force over here, force field, right? It's a vector field on a closed curve, and I'm starting from a random point and ending at the same point. What will be the force done or work done by moving like that? Or a special curve starting from the origin and ending at point 2,1. So let's see how it goes. The work done can be found through a line integral that we had learned already weeks before, and that's my line integral. And I'm not defining the curve yet. That's because I know something. If, for example, I take the derivative of this u by by y, okay, and the first component by y and the second component by x, they are equal. So that should be lighting up some bulbs in my brain. Why? Because if I take my line integral, it's equivalent to the curl, for example, or the divergence. I could add these up and just see. Okay, this is the divergence form, obviously, right? Or let me look at this. Yes, I'm looking at the dv by. Okay, this is the curl form. Sorry, I'm sorry. Second component by x minus the first component by the second y. Okay, so in any case, it doesn't matter. When you add these two up, they add up to 0. So what does this tell me? On a closed loop, if the work expression from the curve form on the right hand side comes out to be 0, then this field must be conservative. And for a closed curve, the line integral is path independent. So, and whether I'm and for the B, now we're going to the B part, it was asking us what is the work now done, not in a closed loop, but if you start from the origin and go to 1. And I'm free now, since I had pinpointed that my vector field is conservative and the line integral will be path independent. Now I'm free to say that I could go from A to B in any path. Okay, doesn't have to be a specific path. I could choose any one. And the easiest one will be going through the axes or parallel to the axes, all right? And that would correspond to something like 64 for the first part and -4 for the second part. Overall, the work would be equivalent to 60 units, whatever those units are, okay? But we could also look at this as a conservative. If I was able to find that conservative field, so the first differential of my vector field is exact differential. This means that there is a field, okay, scalar field on top of my vector field, which is supposed to be differentiable. And if you work out on these two functions, okay, it takes a little bit of time, but you can figure out that they are the derivatives of this one. Okay, it's the divergence, divergence of this scalar field. If the divergence of this scalar field is giving my original field, it's a conservative field. I knew it, and I found this conservative potential function, scalar potential function. So in that case, I'm just going to plug in the A, B values and see the outcome. It's going to be 60. So there's no path dependence here. I'm just comparing the levels of the scalar function with respect to each other, and it should be giving my work. Perfect. I think they're all connected information now. There's a little counter example here. Okay, if I have a force field that is looking like this, I don't know if you noticed that, but I might have some troubles when I hit the origin, right? At the origin, I have a 0, 0, and divided by 0, 0. So there is some infinity type of problem here, which tells me that this vector field is shaky around the origin. Now, I'm gonna do a full circle in this field, counterclockwise direction, starting from point 10 and rotating all the way around back to point 10. And I could do the polar coordinate integrations. All right, so you can look at these on your own in the slides that I will distribute later. The work will be 2 pi's according to our integral form, okay? Line integral form, which could be taken easily by parameterizing and seeing it. And then if I define these as u and v's of my field, I could take the derivatives with respect to y and x. Well, in this case, the right-hand side is more difficult compared to the left-hand side. That's how we use the Gauss theorem, actually. If one of the integrals is difficult, you switch to the other integral. This, we could do it, but there is another problem here, and the work that I get from the double integral comes out to be 0, which was supposed to be 2 pi's. Okay, according to the plane line integral formulation. This is in contradiction, and this is what the reason is. I have a violation of the Green's theorem at the origin. Okay, at the origin. And this origin is a point in my region, so there's a problem. I cannot really define perfectly. The curl of f at the origin is 0, but the field is not conservative. Okay, it doesn't represent a conservative field. So you can understand that by drawing the field. Actually, my field doesn't come out to be as expected, okay, or as usual, as we had seen before. Now, all right, I had talked about this divergence theorem of Gauss. It's just a 3D form of Green's divergence form, and by intuition we talked about it, and by derivations we had talked about it. I'm not gonna spend too much time on this. This is just equivalent of what we have here. And then let's try to define it. I need a closed volume, okay? That's the trick. If you have an open volume, you need some additional tricks to close it. If you are wondering about the flux, let's say, out of a surface, and this surface is enclosing a volume then you're lucky. You can use the Gauss theorem as you like it, and as long as your surface is closed and if they're piecewise smooth and so on and so forth, orientable, which means that um, I can define the inside of the volume and outside of the volume without any problem, okay, without any hesitation or ambiguity. Now, and those are my definitions. Now let's see an example here. I have a position vector r, okay, position vector r, which is scanning the surface that I have, okay, and I'm gonna claim that this volume that is enclosed over here is gonna be like 1/3 double integral on the surface, okay. A surface integral is representing a volume. So you can immediately see that this has something to do with the um, Gauss theorem or divergence theorem in 3 dimensions. And the reason is I can understand, like this is in planimeter, okay? If you remember the planimeter we had here, we could use the divergence, sorry, took a lot of time. Divergence theorem in 2 dimensions could be used to get a formula for surface area of any curve that I have, and if my kind of curve is a surface, actually I can talk about now the volume inside it, and this is how we derive the formula for volumes of different shapes, even a sphere. Okay, so this is how it's driven, actually. So in this case, what is our representation coming up to? Actually, our cosine, or in this case, I could take the position vector as a field vector. Okay, so instead of that, I replace that. And on the right hand side, I have and what's the divergence of my position vector for any random position? It's like x, y, z coordinates. Its length is this, and its divergence is exactly 3, right? Because I have x, y, z dotted with the operator nabla, I will get a 3. And the right hand side is very obvious. 3 dV, it will be 3 V's. 3 V's. And where does the other components come from? I'm going to multiply the R by N, okay, R by N for my left hand side, if I was supposed to do that. The left hand side is always actually for my uh, definitions, okay. R is my position vector field, N is the surface normal, and that will be corresponding to R cosine theta, and R cosine theta ds is going to be my surface integral. It will correspond to 3 V's, okay, and that's our proof. Now you can define the outer normal to the surface as the cosines of that normal with respect to the axes. Okay, so that's a very general definition. If you dot that with my position vector, this is the expression you get, and that in the end, if you integrate by ds, so we're dealing with the B question here. Okay, we're trying to prove this one, and that will be equivalent to our expression, actually. Why? Because the projection of our little piece of ds onto the planes is actually represented by here, and that you can sort out by referring to the projection of an area on the Cartesian coordinate planes. Actually, maybe I should add that note here. Okay, and each individual over here is gonna be equivalent to volume. So you could look at the problem from any direction like that. Now, if my vector function is a simple function like this, and I want to evaluate the surface integral, which is like a flux, maybe, okay, from that surface, and so I'm going to be evaluating a surface integral here, and the surface is going to be a half sphere, or yeah, hemisphere, okay, and I have a surface normal, obviously, and but this geometry is not a closed geometry. Notice that I have a hole at the bottom of it. So how do I do that? I'm gonna be putting another surface to the bottom of it, and I'm gonna be doing two integrations over both surfaces, like S1 and S2. Now, and I need to find the normal of S2 too. It's just defined as the minus K because it's just pointing downwards. The divergence theorem, I could be writing that in two segments, as we said before, and in this case, the right hand side is on the left, so don't mix that up. So I have my volume integral on the left, and the surface integral on the right hand side. And if I look at the volume integral, my field was just x and y, right? X and y. So what's the divergence of that? It's just 1 and 1, so it's right here 2. So two volumes is going to be equal to, now for the surface I have here, surface 2, the dot product gives me a 0, so I don't have to deal with it, but this is the one that I didn't know, right? This is the one that I didn't know, and that will be just equal to 2v's because of my divergence theorem. So it's handy because the hemispherical surface would be kind of difficult to integrate over, but I have a very simple expression of my vector field on the divergence side, and that is going to be equivalent to 2v's. And 2v, I know that the hemisphere's volume is by definition 4 over 3 pi r square r cubed, and taking half of that, I'm going to end up with my integration value in that field. So if I'm that's basically my flux of my field from that surface, right? That's what the surface integral is about. Stokes theorem. Let me move back to the notes to get a feeling of Stokes theorem. I have the kind of 3D form of the Green's theorem, but in curve form. Okay, so in 2 dimensions, we had these alternative forms, and the k was pointing upwards. Remember, it's just to make the curve of f taking the magnitude of that, I dotted with the same sign, same sense vector. Okay, and if, for example, you don't see a k in many other representations, there's a tendency to drop this k because it's intuitive, okay, and that's kind of implied. When you don't see it, it's there actually. Now, instead of a line integral around the curve in xy plane, if, for example, our curve is residing in a three-dimensional space. So instead of a two-dimensional curve, I have a three-dimensional curve, okay? And let's say I'm gonna again move in counterclockwise direction, and I have a vector field that is also in three dimensions. So everything is carried onto three dimensions here. And in that case, I'm still interested in my line integral in my vector field, but the surface that I'm integrating over is gonna be S instead of R. Okay, R was in two dimensions, but S is in three dimensions. And instead of K, I now dot it with my normal vector because I'm interested in curl and I want to make it a number instead of a vector, and the curl is always straight normal to the surface at a point. And at a point, let's say at this point, if I'm interested in this point over here, the curl is pointing up in the normal direction, and obviously the surface normal is pointing up in the normal direction, and their dot product gives me the magnitude of the curl in the normal direction. And instead of general A expression here, I have the surface ds term instead of dA. So these are the little changes we have. And to make it more understandable, we can imagine two cases. I have a loop of wire which I dip into a soapy water, and there's a soap film that is forming, and it was maybe in two dimensions. This wire, it was on the floor maybe. I picked it up to my hand, dipped into the soapy water, and twisted in any direction that I want. So my plane is now moving in three dimensions. That's what we're interested in. And my surface normals are pointing upwards, obviously, and curl dotted with the surface normal, and they point in the same direction. So I'm interested in a number here, not a vector. And in the case 2, it's a very similar thing, but I'm now blowing from one side of this wire that has a soap film on it, and blowing it up a little bit. I'm not making it a complete bubble yet, but I'm partly blowing it inside it, and carefully doing it so that I'm not breaking it. If I blow it a little bit, let's say this much, or more or less, it doesn't matter. I have still the normal vectors to it, to that surface, and that surface is now a different equation. It's not this surface, but still I'm gonna be able to look at it as an equivalent flux integral, right? Because the flux of air molecules that are coming in is gonna be kind of equal or limited by the area I have over here in the wire loop originally. So whether I have a film of soap or a half blown bubble or quarter blown bubble, it doesn't matter. I'm taking the flux of air field that I'm blowing in from this opening over here. So this has an interesting result. So the flux coming out, you can assume that, okay, the flux of atoms that are or the points, the particles that are that have a tendency to move outwards is going to be the right hand side of my expression, okay, and it's going to be equivalent to taking the line integral around the open end of that surface. Okay. In this case, there's no open end, it's a field. So I'm just taking the line integral around it to understand the flux around the surface. But over here, I have a complex shape. It doesn't have to be a regular bubbly shape here. It could have been anything. Maybe I'm not going to destroy my nice drawing here. Sorry. I'm gonna go down and give that to you here. It could be maybe a regular opening, but any random surface after that. Okay, so if I'm interested in flux from the surface, it's actually equivalent to taking the line integral around its opening. So this is very advantageous in many complex situations, right? And that's what's explained here. I have, let's say, a very irregular surface, and it can be considered or calculated as a line integral along the curve that constitutes the open end border of our surface. And the sign convention, let me cover that up over here too. Let's say I'm moving in this direction on the curve. Okay, this is my person, and the our head is going to be pointing up in the normal direction, and our surface could be any surface on top of that. Okay, and the convention is that the positive sign will be my head is pointing upwards. If I was pointing downwards, then it will be the clockwise direction and it will be the negative direction. You could remember it this way. If you have a PET bottle, let's say you're opening it up, and you know the screw principle, the counterclockwise direction will move that screw up, and that's our positive direction. Maybe I'm missing that too here, and this counterclockwise is our positive. Okay, so that's pretty much what we have with the three-dimensional form of our Green's curl form or Stokes theorem. It has many uses. Now, I'm not going to repeat what I have been saying all over the handwritten notes, and these are just again repetitions. You can see that I have a kind of an open volume, right? In this case, I don't have a closed volume. It's like a surface that is bent and forming a volume inside, but it's not crossing over itself. That's the idea. I have an inside and outside without any ambiguity. I don't have any doubt about the inside of this object or the outside of the object, and it's not intersecting, simple, closed, and piecewise smooth. So this is good. We could have many applications of that. Just an example here. Let me put my observer here. So according to that observer, we are traveling in a counterclockwise or clockwise fashion. Actually, we are traveling clockwise fashion with respect to that observer. So keep that in mind. But in any case, I'm traveling in a field like X, Y, Z, J, a simple one maybe, but along the curve C, since I always have, and I need to do it piecewise because it's not continuous, I always have a zero component, okay, a zero component in my curve that I follow. It would correspond to a zero line integral, because the curve dotted with my f is gonna be a zero, right? I always have a zero component in my field along these curves. So in that case, if I have to look at the right hand side, so the line integral has to be 0. Okay, I'm trying to maybe prove that. The curl is something you can calculate the curl actually in 3 dimensions for this function. It's gonna take a little bit time. And let's say I'm gonna prove that this line integral is gonna be represented by those surfaces that I have there, like a blown up, but in a geometrical form. You can maybe think about that as like blow molding in casting, and the mold you have has a very triangular shape like the or pyramid tetrahedral shape like this. So according to Stokes theorem, the right hand side, let's have a look at the right hand side whether it's 0 or not. I need to take for all of the surfaces this into account and do the um, curl dotted with normal operation there. All of them comes out to be 0, and the line integral was 0 also. That proves me that the theorem works. Stokes theorem works. So there could be lots of other applications of it. For example, I have a very irregular shape that I could still define, or maybe not able to define, right? But the flux from it can turn into a line integral. That's advantageous. Maybe we will use that identity to ask you questions on that too. Okay. So obviously there will be a question on divergence theorem and in their two-dimensional form. So I think I have covered about 5 topics here, right? 5 distinct topics. So Green's theorem in plane curve form, divergence form, and finding volume and area by using these theorems for general geometrical shapes, and then Stokes theorem and the divergence theorem of Gauss. Okay, so this concludes our discussions on vector calculus. Thank you. Bye.